So good morning, everyone, and thank you, sir, for that introduction. Welcome to my defense for my work hiding object sizes with constrained padding in multiple settings. So I'll begin today with an overview of what it is that we set out to do with this work. And then after that, I will then cover the different settings that we covered with this work, beginning with the objective. So at a high level, we have a client who is retrieving objects from a trusted object store. These objects, when they are retrieved over the network,
Hey, Andrew, I can't see your slide, so I don't know. 1 second. That's good.
Is everyone else able to see slides?
All right, it's probably on my end. All right,
Yeah.
hang on.
Yeah, no problem for me.
Yeah, go ahead. That's weird.
So we have a client who is retrieving objects from a trusted object store. These objects are encrypted. However, they may have varying sizes. And so the adversary in this setting is a network observer that knows all of the objects and their sizes on the trusted object store and wants to identify which objects the client has retrieved. Now, in this first setting that we consider, we make the assumption, the simplifying assumption, that object retrievals are independent from one another. If the client were to retrieve multiple objects, the follow-on objects are independent from what has been retrieved previously. So then we also consider the setting where object retrievals are in fact dependent on one another, depicted now on the trusted object store by these dependencies that result in possible sequences of object retrievals. In this setting, the network observer also knows all of the possible sequences and then seeks to leverage its knowledge of these dependencies to again identify what objects have been retrieved by the client. So in words, the threat here is a network observer, again, can tell the sizes of objects that have been retrieved and wants to identify which objects have been retrieved. In the dependent setting, this adversary also knows all of the possible sequences and how often they are retrieved. The trusted object store's goal then is to compute a padding scheme. So padding is additional noise data that can be added to an object prior to sending it back to the client, so to hide its actual size. The object store wants a padding scheme that best thwarts this adversary, but then also controls the per object overhead due to padding. Note in our scenario, the object store is only willing to add padding to those objects that have been requested by the client. What this object store is not willing to do is inject decoy objects into the stream. And so our approach then is to minimize various privacy metrics. We consider for the independent retrievals setting, we consider minimizing mutual information between the random variable for object identities and their padded sizes. And we also consider the metric known as Simpson mutual information of order infinity. In the literature, this is also referred to as min capacity and maximal leakage. For the remainder of this presentation, I will just refer to it as I infinity for brevity. And then in the dependent retrieval setting, we again consider I infinity, but now over sequences of object identities and their padded sizes. We also have a constraint on our padding schemes. No object should be padded by more than a multiplicative factor of C specified by the object store. This value for C is greater than 1. So for instance, a value of 1.05 would mean that the object store is only willing to add padding up to 5% of whatever the original size of the object was. And we also want to ensure that objects are served in full. Now, it is possible, given these constraints, that an object could remain isolated in our setting if there are no other objects within this maximum padding factor to which it could pad. Then when that object is retrieved, it would be identifiable to the adversary. So then why did we choose these two metrics? So beginning with mutual information here, we see that mutual information can be calculated as the entropy of the difference between the entropy of S, the random variable for object identities, and also the conditional entropy of S, given Y. Now, this is advantageous for our setting because since the random variable for object identities is constant, minimizing mutual information will thereby maximize this conditional entropy. And we have this relationship where the conditional entropy of S given Y actually serves as a lower bound for guessing entropy. And this is advantageous for our setting because guessing entropy models an adversary who gets to observe a padded size Y and then makes a guess as to what its identity is. And it will make this guess based on what is the most likely object given that size. If it's wrong, it will then continue to guess. And so guessing entropy captures the average number of guesses across all of the objects that an adversary would have to make. So in this setting, we would like the adversary to have to guess more often to be correct. We also consider I infinity, which is advocated by multiple researchers in the literature because it provides a variety of guarantees. For instance, I infinity serves as an upper bound for mutual information across all distributions of object identities. And then also another property that I infinity has is the adversary learns something about object identities as it observes padded sizes. So there's this gain in information based on its observations. And so I infinity also serves as an upper bound for this gain for anything that the adversary could be interested in learning about objects after observing their sizes across all distributions of object identities. So it's a very robust privacy measure. So now I will begin with our solutions for the independent object retrievals setting. So for mutual information, we actually have two subsettings, so to speak, for padding algorithms that could minimize mutual information. Beginning with this first setting, where an object store is only able to pad objects once, perhaps because they're being distributed across content distribution networks. So we refer to this setting as per object padding, and so our algorithm here is referred to as POP. The key insight here is, in addition to this previous calculation for mutual information, we also have this other calculation that shows it's the difference between the entropy for padded sizes and then the conditional entropy of object sizes given padded object sizes given their identity. In this setting, then, because it's per object padding, this term on the right goes to 0, and so it's sufficient just to minimize the entropy of padded sizes. And we show in the dissertation then that given that we are seeking to minimize entropy of padded sizes, we show that whatever the optimal padding scheme will be, it will consist of a partition of contiguous blocks. So what does that mean visually here? I have an example of object sizes, and let's say the padding factor is 1.05 in this setting. It would not be the case that whatever the optimal padding scheme is, it's not going to be of this form here where we have these padded sizes interleaved with one another. It would instead look like something along the bottom here, where again we have these contiguous blocks of padded sizes. And then given this form, we provide a dynamic programming algorithm that runs in quadratic time based on the number of objects available on the object store. We then also consider, again, for mutual information, the setting where the object store is, in fact, able to pad objects as they are being requested each time they're requested by a different client. And so we refer to this setting as per request padding. And we show in the dissertation that in this case, this is actually an instance of rate distortion minimization originally proposed by Shannon. And so due to this, we can leverage an iterative algorithm due to Blahut and Arimoto. An input to this algorithm is a distortion function, which measures the distortion between a padded size and its original size. And so we can leverage Blahut Arimoto in this setting by specifying for this distortion function if an object can be padded to a particular size, then that is annotated as 0 distortion. Otherwise, if it cannot be padded to the size because it's either smaller than its original size or greater than that pad factor, then it's specified as infinity. This then allows us to leverage Blahout Arimoto for this setting. And then also here in the independent retrieval setting, we consider I infinity. Now, the solution here for I infinity actually results in a per object padding scheme. So there's no separate algorithm for PRP versus POP. It's just one algorithm is sufficient for I infinity. And the calculation for I infinity does not actually require the distribution for object identities. And so that's where it gets this name, padding without a distribution. We refer to it as PWAD. So the solution here is an algorithm that runs in linear time. And so for this same subset of objects here, you can visualize PWAD as running from right to left in a greedy fashion, starting with the largest size 115, and then adding objects to the 115 padding group until it then gets to 109. 109 could not be padded to 115 for this value of C. So then 109 becomes the next padded size, etc. So then for our evaluations in this first setting, we use two different data sets, one consisting of Node.js packages and another consisting of a collection of images from the Unsplash website. The data set is known as Unsplashlight. And what we present here are some sample padding schemes given 10 selected images from the Unsplashlight dataset, just to show what these padding schemes look like. And so each one of these padding schemes on the y-axis here, so on the left, these labels are the pictures, and then across the x-axis here, the rows then represent the likelihood that if you were to retrieve a particular picture, how often would it be padded to a particular size? So we see for our POP and PWAD algorithms, these are both deterministic. So there are only single entries in each row, 100% probability they're going to be padded to those sizes. PRP instead is a per request padding scheme. And so we see in some instances the distribution being spread out across possible objects here. And what's interesting to note in this particular subset of pictures, because of this, there's no object here, there's no picture that's completely isolated. There are at least a couple other objects for each size that the request could have been. For instance, if a client were to request picture 3 here, 19% of the time, picture 3 would be padded to the size of picture 4. The other 81% of the time, it would be padded to the size of picture 8. We then, for this first setting, compare to 3 algorithms from the literature, dalpaca, palpaca, and padme. dalpaca and padme are both per object padding schemes. So we see, just like POP and PWAD, they only have entries of 1 for any given row. palpaca is a per request padding scheme. And so as part of our evaluation, we, for each data set, our Node.js data set and our Unsplashlight data set of pictures, for increasing values of C, we used each algorithm to produce a padding scheme for the given data set, and then calculated both its resultant mutual information and also its result for I infinity at each value of C. Note, though, that Padme, one of the competitors from the literature, does not take a pad factor as input. And so what we did was we ran that padding scheme on the data set and then calculated what was the largest pad factor given that data set, given that algorithm. And then we plotted it where it lies as far as its value of C. So we have it plotted here at 1.09 on Node.js, 1.03 on the Unsplashlight data set. For each one of these clusters of results here, the bars extend to the result that the padding scheme yielded for mutual information. And the error bars or the whiskers extend out to their results for I infinity. And so in general, what we see is from right to left here, so lower values are better. Within each cluster of results, PRP yields the best results for mutual information. Unsurprising because this algorithm is optimal for that setting. What's perhaps most interesting here is that our POP algorithm, per object padding, beats P-alpaca from the competitor from the literature across the board here. It's interesting because P-alpaca, being a per request padding scheme, is not limited to being deterministic, and yet POP still does better as far as mutual information on these data sets. We then see PWAD doing fairly well for mutual information. D-alpaca and PADME generally are not competitive. Then when we look at the results for I infinity, now we see PWAD doing the best across the board. Again, unsurprising, it is optimal for I infinity. We then also conducted evaluations for recall and precision to put this in a more operational setting. So for these evaluations, we first created subsets of each data set to mimic an adversary who is interested in some of the Node.js packages or some of the Unsplash light pictures. And so the adversary seeks to guess, is this, after observing a padded size, is this or is this not part of the subset of interest here? And so for increasing values of C, we have the recall and precision results plotted. The way that each one of these charts for a given algorithm is plotted by calculating the recall and precision for increasing confidence levels that the adversary has for each one of the subsets it's trying to detect. Overall, we can see that D-alpaca and PADME, not competitive. POP, in many instances, clearly in the lead. So for these results, being towards the bottom left are better. So we see PRP in many instances clearly in the lead here. And we also see in many instances our other two algorithms, PWAD and POP, also very competitive. And then finally, for this setting, we also calculated the runtimes required for each algorithm to produce its resultant padding scheme for increasing values of C. Note that neither PADME nor D-alpaca are plotted because those are just pure functions. They do not need to pre-compute a padding scheme for a given data set. So the results here indicate PWAD, very fast, barely noticeable above the x-axis here. Linear time algorithm, very efficient. The next best, as far as time, we see P-alpaca running fairly fast, POP in third. And then we see that PRP takes longer to yield a padding scheme. But we show in the dissertation, though, that we show a technique for after PRP calculates its initial padding scheme, we then show a technique to more quickly update the padding scheme incrementally as perhaps object sizes change or the distribution over objects change, etc. So once the initial padding scheme has been calculated, we then show this line here with the longer dashes. It can be updated much more competitively incrementally. So then now I will transition to our dependent object retrievals setting and cover the solution that we provide for padding in this setting. So in this setting, we provide a linear program that we named padding for sequences, or PFS. It takes as input the set of objects as well as the set of possible sequences on the data store. Again, takes in this max padding factor. And then also we have an efficiency parameter, which we label K, that serves to reduce the dimensionality and reduce the number of constraints required to run the linear program. Its output then is a memoryless padding scheme that minimizes an upper bound on I infinity for sequences, and like all of our algorithms, does not violate this padding factor C. Memoryless in this setting means that as a client continues to request objects from the object store does not need to remember what objects have previously been requested, nor does it need to remember how it padded those objects. In this setting, then, we compared to various algorithms from the literature. The reason we selected these algorithms is because each one of them targets a different privacy metric. BDK from the literature targets mutual information for sequences. MVMD targets L diversity. And PWAD from our previous setting targets I infinity, but again, for the independent objects setting. And we see for the algorithms that work for sequences or are designed for sequences, BDK, MVMD, and our algorithm PFS, our algorithm requires the least amount of inputs, or in other words, the object store needs to know less than the competitors in order to run our algorithm. Now, as part of our evaluation, we constructed 3 data sets for this setting. A data set consisting of web pages from the Linode documentation site, also a subset of articles available on Wikipedia, and then also autocomplete results. For the purposes of today's presentation, I will cover the autocomplete data set and then show a subset of our tests that was conducted on the autocomplete data set. In the dissertation, we also conducted evaluations where we evaluated our algorithm against each one of the competitors against their metric. I will show you today the results of the calculation, the evaluation against I infinity for sequences. So this data set, autocomplete, consists of 899 words, where each one of the entries in the data set represents a client who is at the Google search field typing consecutive letters of each word. And so as you type letters into Google search, you receive these updated search suggestions based on what letters you've typed so far. Each one of these search suggestions is sent back with a perhaps different size. And so this then, for the word tree, for example, the sequence would be the progressively longer prefixes of the word, and then the responses then, the search suggestion updates, so to speak, their sizes, that's what the sequence of sizes is in this data set. And so to evaluate each one of these algorithms for I infinity, what we did was we ran each algorithm to produce a padding scheme, and then applied the padding scheme to the entire data set and calculated the resultant I infinity for progressively longer sequences in the data set. So as the sequence length increases, we have these cluster of results here, where from left to right, each bar represents BDK and then MVMD. Now note the 3 here. MVMD is designed to run with a different target for L diversity. So when we annotate the number here, that indicates what L diversity was given for a target. So MVMD 3 was run with the goal of ensuring L diversity of 3, L of 3. And so as the sequence lengths increase, we have these bars here for each one of the results, each one of the algorithms. But then also now, our algorithms PWAD and PFS take as input C, the pad factor. Neither BDK nor MVMD take a pad factor as input. And so then what we also did for PWAD and PFS is we ran each algorithm on the data set with progressively larger values for C. And so for 1.05, 1.25, and 1.5, we have the results depicted as these vertically stacked bars. And then also on the right here, we calculated for each one of the resultant padding schemes, we applied the padding scheme to all of the objects in the data set and calculated for all of the objects, what was the worst case padding factor applied to any object. That's denoted here as C max. And then we also calculated the average pad factor applied to all of the objects given that padding scheme, plotted as C average on the left here. And so as I move back through these results for PFS, we can see here the individual results for the resultant max pad factor and average pad factor. This is most interesting when we consider our competitors here because they, again, do not take a pad factor as input, so we calculate what their pad factor is after the fact. So now, to more easily compare these results, what I've done here is kind of frozen the results, so to speak, on one value for C, 1.25, and then use this color scheme here to highlight where on what the resultant I infinity was for each one of the results. We can easily see that BDK uncompetitive. We can see that NVMD started off uncompetitive and then improved for the increasing sequence lengths. But across the board, we can see PFS doing quite well for a C of 1.25 here, beating NVMD mostly across the board as well as PWAD. But the key here is this is for a particular value of C, 1.25. So when compared to NVMD3 and BDK, we can see that for this data set, they yielded much larger pad factors in the worst case for this data set. So PFS doing better for I infinity, and then also by design, constraining the amount of overhead applied to the objects on the data store. Now, it's the case, though, that the number of sequences possible for a given object store increases exponentially as the sequence length grows. And so it can be, in some cases, infeasible or difficult for an object store to run PFS on all of the sequences. So then what we saw was a solution where, what if an object store can't run PFS on all of the sequences? What else could it do? So we then also present for this setting an algorithm that we dub PFG, padding for graphs. It leverages the same underlying linear program with the caveat, instead of providing the linear program the set of sequences, you instead provide it the edges, where the edges are all of those subsequences of length 2. So you can think of them as directed edges from one object, then the second object is retrieved. Provide all of those to the linear program instead of the full sequences. And so the insight here is, when we model the object store as a graph where the objects are the vertices and the dependencies are these directed edges, then whatever the full sequence, the full set of sequences is, it's a subset of the walks on that graph. And so we ran both of our PFG and PFS algorithms across all three data sets for increasing values of C to measure their runtime. We also measured across two different values for K, which was our efficiency parameter. And we can see that PFG in most cases here, especially when the runtimes are quite large for Wikipedia and autocomplete. Note on the left and right charts here, we've got logarithmic scale on the y-axis. PFG runs much faster, in many cases, orders of magnitude faster than PFS for the same K. And then we also see that PFS for autocomplete, for instance, on our test machines, we were unable to complete a run at a pad factor of 2 because of the memory requirements. So again, PFG designed to be more efficient than PFS, especially when the full set of sequences is not known to the object store. So then we also compared what's the impact on I infinity if you leverage PFG versus PFS. So that's what these charts depict here. We depict autocomplete and Wikipedia. And so on the left of each one of these pair of columns, these bars, PFG is on the left. And what's interesting is that for these shorter sequences, we actually see a trend where PFG is resulting in lower I infinity. Maybe unsurprising because PFG is given as its input short sequences. It's given all of the subsequences of length 2. However, as we move to the right here for increasing sequence length, we can see that PFS then starts to outpace and do better for I infinity than PFG. Again, PFS having been provided all of the full length sequences. Still, though, these results show that PFG could be leveraged by an object store to certainly reduce I infinity if it's unable to produce the full set of sequences. That then brings us to the final setting that we consider here. It's actually still, we still consider the dependent object retrieval setting. But what we seek here in this final portion of the dissertation is, can we perhaps leverage something other than a linear program for this setting, padding for graphs? So what we sought here was, perhaps can we leverage a derivative-free optimization technique for this setting? And we ended up leveraging differential evolution. I will explain in a couple slides from now why it was so well suited for this setting. So the key insight here is I infinity for sequences can be upper bounded by a term that's only dependent on the number of possible padded sequences on the object store. Furthermore, we have this relationship here from Taubig that for a particular length of sequences, so M here, all of the M length sequences can be upper bounded by a term that is dependent on, first, the number of padded sizes on the object store, and then also the in degree and out degree of each one of these padded sizes. So if you imagine the object store becoming a padded graph after padding has been applied, you have vertices now are padded sizes, and dependencies then become directed edges between those padded sizes. So we then sought a solution that minimizes the number, so the sum of vertices and edges in the padded graph. And to make things a little bit simpler in this portion of the dissertation, we adopt some additional notation where the union of the objects and their dependencies then becomes this S sub G for graph. You apply padding to those objects, they then become this notation Y sub G, the padded graph. So to better depict what's happening here, if you have a data store, an object store of objects and edges between them, what does it mean to then apply padding and become this Y sub G? So for this example, I'm again using the very same sample set of objects, but I've now applied labels here, A through G, and then also I've designated some directed edges between them. Visually, this is what that object store would look like down here if turned into a graph. Given these directed edges, there are three sequences of length 3. And then so this S sub G consists of 7 objects, 6 edges, and so the sum of this set is size 13. And so what we seek to do then is minimize this number after padding. So on the right, what I've depicted are 4 example padding schemes, all for the same value of C, 1.05. they are arranged from top to bottom in progressively better padding scheme solutions. So for instance, starting at the top here, this padding scheme results in 3 padded object sizes, 105, 109, 115, and results in 5 padded edges. So this is an improvement from what we started with. There are now 3 objects, padded object sizes, and 5 edges for a total set size of 8. However, it has not improved, it has not reduced the number of possible sequences. There are just as many possible padded sequences as there are unpadded sequences. And so then we move down further. This next padding scheme, yet again, another improvement. It's now reduced the number of edges down to 4. So a resultant set size of 7, still though 3 padded sequences. We then get to the third padding scheme here though, same set size, but it in fact does reduce the number of sequences to now 2 padded sequences. And then finally, we arrive at what's actually the best padding scheme for this object store. You can get the number of padded edges down to 2, so a set size of 5 now, and it reduces the padded object sequences down to 1. So overall, what this demonstrates is if you can reduce the number of padded objects and padded edges in this padded graph, you can reduce the number of possible sequences at this object store. So then, why did we use differential evolution? What makes it so well suited? So I'll begin first with a slide that visually depicts how does differential evolution work in general, the general default framework. And then in the next slide, what I'll do is I'll show the design decisions that we implemented that make differential evolution so well suited for our problem. So along the top here, differential evolution, like many other derivative-free optimization schemes, such as particle swarm optimization and genetic algorithms, maintains a population of candidate solutions. So I've depicted those along the top here as padding schemes. And so there is this outer loop here that will continue until some stopping condition. That could be either number of iterations, or it could be the entire population has converged on a particular value for the objective function, etc. What I will focus though on is what happens inside this loop. So inside this loop, there is an inner loop that iterates across every single member of the candidate solution population. And the first step inside this loop is to first create a mutant solution. In the default framework, this mutant solution is created by first randomly selecting 2 solutions from the current population, taking their difference. You then multiply this difference by an input parameter called the mutation constant, add that to the current best solution among all solutions in the population. You then arrive at this mutant solution. Then a trial solution is created by merging the components of the mutant solution with the ith solution in the current population, and that merge is done in the following way. For each one of the components in the mutant solution, you select a random number from the range 0 to 1. I like to think of this random number, though, becoming a weighted coin toss, because this second parameter here, crossover probability, you then compare this random number to the crossover probability. If it's less than this number, then you select that component from the mutant solution. Otherwise, you select the component from the ith solution. So you flip this coin once for every component, decide which one you're taking. Are you taking that position from the mutant or the ith solution? You then have a trial solution. And then now, if the trial solution results in a better value for the objective function, then does the ith solution. That trial replaces the ith solution, and you continue for the next member in the population. Once you've done this, you then update the best solution in the population, and you continue again. So then, how did we leverage, what design decisions did we make that allowed differential evolution to work so well for this setting? So first of all, differential evolution, like many optimization schemes, suffers what's known as the curse of dimensionality, where as you increase the number of components in your solutions, the search space becomes so large that it becomes hard for the algorithm to find an optimal solution. So we reduced the dimensionality by making it so that every solution, every candidate solution is not a padding scheme for every single object on the data store. It's only a padding scheme for what we refer to as the anchor sizes. So for this very same sample set of objects that I've shown previously, for 1.05, the anchor sizes, you start at 100, you then keep increasing until you get to a size to which 100 could not pad, so 109 in this case. 109 becomes the next anchor, etc. You wind up with 100, 109, and 115 as the anchor sizes. So then given these anchor sizes, what I depict here are 3 potential padding solutions that you could leverage. So 100, in this first example, 100 pads to 105, 109 pads to 110, 115 pads to itself. This then gets turned back into a full padding scheme in the following way. You pad, so for instance, 100 padded to 105. So 105 stays at itself, 109 padded to 110, and then everything else pads up to 115. In this second example here, 100 didn't get padded. It stayed at itself. So then 105 pads up to 110. And so what I show in this third example then is 100 did not pad up to 105. 109 padded all the way up to 114. So then that left 105 isolated. It cannot pad up to 114. So this then is a suboptimal solution here. This scheme has left a non-anchor size unpadded. So I show this because what we see is there's this synergy when you have a good padding scheme for the anchors, they aren't leaving the non-anchors between them unpadded. So we want to preserve that substructure where contiguous anchor sizes are yielding good solutions. So there's a second way to run differential evolution called exponential crossover, where you do still flip a coin for each of the components, with the caveat, once you flip a tails, so to speak, you then stop flipping the coin and you take all of the remaining solutions or components from this ith solution. And so what you wind up with is you wind up with a trial solution that consists of a contiguous portion of the mutant combined with a contiguous portion of the ith solution. So you preserve this substructure where neighboring anchors have arrived at good solutions that are not leaving sizes unpadded.
Andrew, sorry to interrupt, but maybe wrap up in 5 minutes or so?
Yes, sir. Yes, sir. So for this evaluation, we continue to leverage our Linode and Wikipedia data sets. We also introduce a Netflix data set. What we did in this setting, though, is we expanded it so that we include in our consideration all of the simple paths at a sequence length. So we can see this results in data sets that are quite large. And so to evaluate our differential evolution solution against the linear program, we conducted tests where we increased values for C and measured how long did it take the algorithm to yield a padding scheme, and then also what were its resultant values for I infinity. And so the LP we have plotted as these X's. So in many cases, they ran in such a similar time frame, the different values. We ran this 5 times each, and so it can be hard to see that there's a little bit of a difference in the time there. We are able to plot the 5 runs of differential evolution as lines, though, because each time through that outer loop, when it calculates what is the best solution at a given time, we can extract that solution and calculate its resultant I infinity. So we see from these results depicted here for the Linode data set, not only does differential evolution start to yield results faster than the LP, but they're competitive and in fact a little bit better than the LP. But I will note though that the Y scale here is pretty tight. They are both very competitive algorithms. Our main intent here was to design an algorithm that is faster and more efficient than the LP. And so as part of that efficiency, we also evaluated how much more memory does the linear program require than differential evolution. So along the top here, we have those plotted as ratios, and we see that in some cases, the LP requires almost, if not more than twice as much memory than the differential evolution solution. And then we also compared what happens as the data set increases in size. So we leveraged our Netflix data set. We added one sequence at a time, and we depict here that the memory requirement for the LP outpaces the memory growth for the differential evolution solution. So in conclusion, I would like to thank everyone here in the call today. In particular, I'd like to call out Pranay for being a fantastic collaborator with this work. Really appreciate all the time you put into this. And then also to all the committee members here today. Each one of you, this journey began many years ago, back in my master's at UNC. Each one of you, you've served either as instructor, mentor, guide throughout this whole process. So I really appreciate that and your patience throughout this process. So in conclusion, we presented solutions to produce padding schemes for an object store that wants to thwart an adversary. We considered a variety of metrics here: mutual information, I infinity, all the while ensuring that objects are not padded larger than a factor of C. We considered the independent object retrieval setting, dependent object retrieval setting, and then also produced solution for the dependent object retrieval setting that is more efficient. Thank you. The floor is open for questions.
Yay. So, as I remember, it's customary to allow public questions first, which really, I guess, means Jason and Pranay, if you want to take a shot at Andrew, here's your chance.
I've been waiting 6 long years for this, so here we go. So I had a question. Can you explain the intuition a bit behind choosing a specific padding factor C and how it practically balances privacy with overhead?
Right. So there are perhaps some scenarios where, so one thing we have to think about is there are clients out there all retrieving objects from the object store. And if we don't apply a per object padding factor, there could perhaps be one client that retrieves an object that was originally quite small, but if that padding factor is not constrained, then that client now unduly suffers because perhaps that object was padded very large. Moreover, the object store gets so not only is every object constrained, but then this also ensures that the average bandwidth increase for all of the objects cannot then also exceed the value for C. So especially in this setting where maybe the distribution is changing frequently, this ensures that regardless of the distribution of S, the object store will never have a bandwidth increase beyond the value for C that it has provided. And this can be quite advantageous for priced connections, et cetera.
So maybe like on like a slight follow-up to that, I guess, right? Or tangential at least. How do you envision integrating the padding scheme into existing systems? What practical challenges do you think arise during its deployment?
Right. So as far as practical considerations, one thing that's actually quite nice about the per object padding scheme is this: if an object store is serving its objects over a content distribution network, it only has to apply the padding once, so that's quite efficient and then it will then work on whatever the whatever that content distribution network, however it works. What the object store would then need to do is ensure that when the client program, whatever it is that is making the request and whatever the object is in that setting, it needs to have a way to peel off the padding, so to speak. This can be done in a variety of ways. You can put it into the client software itself. In the web setting, you could perhaps leverage technology such as JavaScript workers to peel that data off as well.
Awesome. That's it for me. Thank you.
Thank you.
So can I jump in and piggyback on Jason's question? Because I kind of like it.
Yes, sir.
So you at the end of the first section, you talked a little bit about updating the padding scheme in the case of object changes or updates or whatever, and how you were able to reduce the cost of one of the schemes being updating the padding scheme. I guess to me, that strikes me as one of the things that's a problem for these techniques is if you have an object store where things are being modified, how can you keep up, right? In some sense. And I know you didn't do tests with actual traces of object modifications, and if you were to try to keep up, or how well you would do, but what challenges do you see there, or do you think that it can be addressed in some effective way? Like, what would you say to that?
Right. I would say that yes, it is a challenge. In particular, we found it most challenging for those settings where the algorithms relied on the distribution in order to reduce, for instance, mutual information. The algorithm that was that struggled the most with updates was PRP. We did improve it with incremental updates, but still it was challenging. So I would say in practice, the most likely approach, which would be quite efficient, is perhaps leveraging differential evolution, because it can continue to run iteratively. You can extract, if you need a padding scheme, time now, so to speak, you could take the current best from that solution, apply it immediately, and then continue to run differential evolution to try and update the current padding scheme.
So you're kind of envisioning, regardless of what the initial padding algorithm is, PFG, PFS, whatever, using differential evolution as a way to patch it up, as it were, when the object store or the objects get changed as they get changed.
Correct. Correct. And one interesting thing about, so not mentioned in the presentation, but as with any derivative-free optimization scheme that maintains a candidate population, you have to first seed that population with starting points. And so what we leveraged in the dissertation is we actually seed that candidate population with, in the paper, we went with a value of 300, where 100 of those initial solutions are, that padding scheme is essentially running PWAD like from left to right. The second is essentially running PWAD right to left. And then the remaining third of those solutions is just randomly assign the anchors within their limits of C. And so what's interesting about the differential evolution technique is it's actually already starting from a very, we've shown throughout the dissertation that PWAD, even though it's designed for independent object retrievals, still results in many cases with good results. And so in fact, differential evolution is kind of picking up with it starts with like 2 different PWAD solutions and then improves from there. So, it already starts, I would say, from a very strong beginning with differential evolution.
Got it. Thank you.
Thank you.
Hey, Pranay, here's your chance.
No questions from my end, but just wanted to say congratulations on all the great work.
Thank you. I really appreciate it. Thank you for everything that you've done.
Good to hear your voice again, Pranay.
Yeah, likewise.
So I guess with that, let's open up the committee, and I guess the norm is to do who's furthest from the defender, who I guess is Fabian, right? Yeah, you must be the furthest.
Sure.
Because you're in upstate New York, right, Andrew?
Well, I'm in upstate of the city, but still south and overall.
Yeah.
Hey, Andrew. Yeah, I have lots of confusion, so I'll just acknowledge that up front. And so I'll try and tease out some of them as I go through in no particular order. I thought, just as a positive, I thought the earlier parts with the, up to chapters 3, starting 4 were kind of clear in what you were trying to do. And then for me, things went completely off the rails, like really off the rails in that, like PFS, I was trying to understand and motivate for a long time what was going on. So let me get to that one maybe indirectly. So in your analyses, in your, studying this space, how common is it that you've seen that the full set of sequences are not known to the object store a priori? And in these cases, how well does PFF perform over PRP? I try to get a sense of, from a practical perspective, like what's the benefit? And I can't see it in the dissertation yet. So there's a lot of the motivation for PFS was just throwing me off completely, leading other than you showed that at some points the prior solutions were not efficient. And then you completely changed the assumptions on me. And I'm trying to get a sense of what's happening there. So first, how common it is for the full sets of sequences to not be known by the object store, and then tell me directly where you see the benefits of PFS over the prior solutions in your prior work, not the other work, the prior solutions in your dissertation.
Right. So I just want to verify. You said PFS, but I feel like the question was asking more about PFG. The
PFG,
one,
sorry,
yeah,
PFG.
Okay. Yep. So in the BDK work, in fact, the Bacchus et al. Solution from the paper that we compare to, they do, as part of their motivation, their technique is, it's different than ours, but they also design their technique so that the full set of sequences does not need to be known. So there is at least one other competitor there that makes the same assumption. So I would say, for instance,
but kind of none of your examples in the data sets that you have this, right? Really?
well, so I guess it's probably best to, I would say the clearest motivation then is the fact that the number of sequences grows exponentially and becomes infeasible for PFS to run as the sequence length grows. So even when the sequences can be known, which, so for instance, in the PFG chapter, we did enumerate all of the simple paths from each of the objects out to a length of 5. But then that sequence length, let me back up to that slide here. Apologies, let me find the number. It's only a few slides back. So they grow to be quite large. In fact, Linode at a sequence length of 5, despite starting at the lowest number of objects and edges, it grows much faster than even our Wikipedia and Netflix data set. And so even when they can be known, just anecdotally, enumerating these sequences when I was conducting the evaluations would take, on the order of minutes to even fully enumerate the set of sequences so that I could then compute I infinity on them. So perhaps the strongest motivation is just this exponential growth. Perhaps some data stores that then becomes unknowable, but certainly becomes infeasible for any data store at some sequence length.
Yeah, okay. Yeah, I thought that this changing the criteria along the lines of the data store does not know this just seemed very weird. It was very different than anything you had before, but okay, I buy the exponential growth part there. I still think that a lot of the thesis, it's really unclear what are the research problems that you're trying to solve at a certain point, and in what sense that the settings, you use the word settings, but they're not very clear several times, the settings under which, the operational settings under which your solution is most applicable. Like, so if I were to go and want to give your dissertation to somebody who is following up on this work, I can't point to a set of settings and I say, okay, here are the 10 different settings, and here's how to think of these 10 different settings, and this is where, one solution is much more practical over another solution, where I can take that, I can say, let's look at it in terms of actual overheads. Like, the actual overheads are never shown. I have a hard time trying to figure out what are the actual benefits, the actual overheads in some of the evaluations that you did, right? I agree with several of the metrics that you chose, but then when the rubber meets the road, I can't get a sense of, from a practical, from an operational point of view, how much does this really matter yet?
Maybe, can I just, for clarification, are you,
Mhm.
you say overheads, do you mean padding overheads or?
Padding
performance
overhead,
costs?
padding overhead,
overheads, I
padding
see.
overhead, padding overhead. Like, where does it really matter? Like,
So for instance, then let me go to some other padding overhead results that we had from the PFS section. So for instance, for Linode, for instance,
yep.
we have again the maximum. So now we've applied for the Linode setting, we've applied the competitors NVMD and BDK on the Linode data set, and then calculated what were their resultant max padding factors, and then the average padding factor applied to any object. And so in this data set, the maximum and average padding factors applied by the competitors were so large that the results for PFS and PWAD have to be this inset here that results in just this single point on the overall scale. So NVMD, the NVMD set to an L diversity of 3, worst case padding applied to any single object over 5,000, almost 6,000.
Yeah.
With a almost 10 times factor overall. So if a object store wanted to use NVMD, they are almost 10 times they will result in almost 10 times as much bandwidth out the door overall than our solutions, which guarantee for a given padding factor, max or average, since this is being applied per object, you can ensure, let's say the padding factor was 1.05. Not only will no object exceed 1.05, neither will the average bandwidth out the door from the data store. It will also not exceed 5% additional bandwidth.
So I think there are two things here. So I agree. So for the competitors, I think the chosen competitors, I think you're right? That shows the relative overheads. Your gains are clear here. On that, I think the thesis doesn't build. So I'm sure you did this in a systematic way of how you chose what the competitors were. I cannot tell at all. Like, I know this field is huge, and I'm trying to get a sense of, and I haven't followed in the last few years. The last one I looked at was some of the PADME work. There's so much in this space, and then I'm trying to get a sense of, okay, so if I were to pick up your work and say, there's no systematization for me of how did you choose the competitors in this space. It seems in some cases, and maybe that's what you did, and it's fair if that's what you did. You just took the most recent published work at that time and you say that's the best, right? And I don't think that's definitely the case, right? But there wasn't a system. I couldn't find a systematic assessment of, okay, for each one of those settings that I'm looking at, here's what the competitor, here's what the landscape looks like. And here's how I choose representatives in each one of those subclasses in this landscape. The choices seemed very arbitrary to me. So I was having a hard time trying to get a sense of, okay, in some cases I can see that, yeah, you way outperform the competition. But I didn't get confidence in the selection that led up to those competitors. So I think to me, that was really missing, especially given how large the space is, right? And I thought you did yourself a disservice by not explaining that at all. So I had a lot of questions relative to the choice of the competitors. But in the ones that you do have, like in this slide 68, you show an advantage. My second question was though more about in your own schemes, like relative to your own schemes, like where do we see the actual practical impact of the variance that you have? Right? So not the competitors. You have multiple variants of things that you hear that like the practical impacts for each one of these variants. It's very hard for me to get a sense of where the improvements under which settings the improvements really made a major difference in pattern object sizes. And I don't know if you have that in the thesis. Did I miss it? Where should I look?
So for instance, this final setting here, the differential evolution versus the LP setting,
Okay.
we do state that for many instances, the LP performs the results for the LP are very competitive, and in some cases there's not a lot of daylight between the results for I infinity between the LP and the differential evolution solution.
Yep.
However, there are instances such as the Wikipedia data set here where even for these scales, we see that the differential evolution variant is performing much better than the LP. So for instance here, for a value of 2 on the Wikipedia data set, the differential evolution solution algorithm is yielding results much faster than the LP relative here, so sub-second here, and in fact yielding great solutions less than half a second. And then also here, despite having translated this to bits, right? Mm-hmm. This is almost a half a bit less result for I infinity, which is actually quite large, right? Having crushed it to logarithmic scale here with bits, it's still this is considerable daylight between the results here. So
and do you have an intuition of why these wins came in these cases?
So there's a couple factors here. So the LP, in order to run efficiently on the servers that we had and the data sets that we had, we ran with the efficiency parameter for the LP, that K, with a value of 2. That means that at most any object could pad to 4 possible sizes based on how close it is to anchors, etc. So that dimensionality reduction step there reduces the number of sizes that objects could pad to. So it kind of limits the options that LP is presented with. So that is, even though we do have dimensionality reduction also in differential evolution, it's not as constrained because the anchors themselves could pad to any one of their available sizes. So there's more options for padded sizes with differential evolution. And then also, let me go back to so the linear program is designed to minimize an upper bound on I infinity, whereas the differential evolution solution actually minimizes directly that I infinity for a per object padding scheme.
Mhm.
So the differential evolution algorithm not only is less constrained in its dimensionality reduction, it more directly targets I infinity for S sub G than does the linear program. So these are at least two factors why when the differential evolution technique is better, why is it able to produce better solutions than the LP?
So can
And
I ask, just to follow up with
Yeah.
on Fabian's question here? I mean, one version of the question that maybe I'm hearing is, okay, I'm running a server and I have a bunch of objects.
Mhm.
Which flavor of what algorithm should I be using, and is it
And
worth
why?
paying the cost of a sequence-based one versus a sort of a independent retrievals one? I mean, yeah, do you have any inkling as to how to answer that question? That's a
That's
hard
what I
question.
thought I thought his last chapter was going to be, and then I was just looking for this. I was like, I'm where is it?
I mean, so you have cases, Andrew, in your dissertation where you show that PF, oh gosh, the acronyms, let's see.
Yeah.
The padding for sequences outdoes convincingly padding without a distribution, right?
Yeah.
On a synthetic data set.
Yep. Early on, yeah.
Yes, in the synthetic data set, so I don't have that in my backup slides. I could display that or just talk to it in the synthetic
Well,
data.
I mean, I guess I didn't mean to necessarily, well, unless Fabian wants to sort of revisit it. I guess the flavor of what you've accomplished here is that you've shown daylight between these algorithms, but you don't yet have a recipe for, given an arbitrary object store, here's the criteria you apply to tell you which one to use, short of just applying all of them and seeing which one you're happiest with.
Correct.
Right. And I think, is that what you were sort of going toward there, Fabian?
Yes, correct. And I'll tell you exactly why this comes up. Like really early on, I guess I have a little bit of bias, so I should say that early on. So I've always been a big fan of guess and entropy, and then you started early on saying that pretty much, the impact of using, some of the limitations of mutual information is hard to interpret operationally, kind of, so I should start thinking about min capacity. And although I really didn't see the operational impact shown anywhere of min capacity versus mutual information, but you started putting my mind in that setting, like, okay, so I need to think about it from an operational perspective, how to interpret all of this. And then you just lost that thread for the rest of the chapters. Like it just went on into La La Land, and I have no way to come back and say, okay, operationally, here's, what I'm looking at, here's my constraints. Which one of the solutions should I try to implement and why? Like, or do I have to do all? I have no idea, like, in the end.
Yeah, I mean, well, you want to answer that, Andrew?
Yeah.
I can give you what I would say, but that it's your defense. So,
Yeah.
Right. So I would say so when we transitioned from the first setting to the dependent retrievals setting, I did attempt to apply mutual information to the sequential, to the dependent retrieval setting. Only able to provide solutions here though for I infinity. So there's that, able to provide an efficient solution with a mathematical guarantee for what I infinity represents. The other thing too is, so when you transition to dependent retrievals, so if you stick just to mutual information with guessing entropy tells you how well will you do against an adversary that is guessing the secret random variable, which would be sequences under this strict setting here. The adversary is trying to guess exactly the sequence of objects, entire sequence. However, what we get from I infinity, though, is we get an upper bound for any function that the adversary might be wanting to guess about the random variable. And so with the sequential setting here, maybe the adversary isn't interested in the whole sequence, right? In particular, right? Maybe the adversary isn't interested in guessing exactly the entire sequence. Maybe they are most interested in, well, what was the first object? That's a function of the entire sequence. That adversary is subsumed when we consider I infinity, but is not accurately captured when we only work with mutual information. That's the adversary that wants the whole sequence and nothing short of the whole sequence. So I think once you move to dependent retrievals, then the adversary is best described as the adversary that I infinity is defending against.
So, I mean, I guess this is a question of both Fabian and Andrew. Like, Andrew, could you add a discussion in your last chapter that at least tries to address, even if not completely, right, address the question of, okay, put yourself in the shoes of somebody who wants to apply this.
Yeah.
What would you go through to try to decide which one to use, and what, some of the things you just talked about? And Fabian, if you did that, would that be helpful?
I think it's necessary to
Got
me. I'll just add one more context on that he might be able to do, just a thought exercise. What took me down there, and I left it to the other committee. So I was trying to think of I guess one, I'm not a big fan. All those so-called token lens side channel attacks in this space, I just don't find them practical at all, right? So that's something else, right? So you were defending against something that I would say I don't even think that some of these work that's been shown to be practical at all. Nevertheless, people are seeing this as an important problem. So I was thinking, oh, actually, at the same time of Andrew's paper, you had one of them was Usenix 2024, right? If I remember, Andrew.
Yes.
Yeah. There was the token side channel attack paper that claims to read the encrypted responses from the AI assistants, right? The setting is very similar.
Right. Yeah.
Right?
Yes.
Very similar.
I attended that presentation.
Yeah. Very similar. So this is the White and Owl presentation, right? So you have the AI chat models, and they're trying to reconstruct the prompts. And they have a set of pattern-related defenses. And so I was looking at the operational setting for that work. I'm like, okay, so if I take Andrew's work, which one of Andrew's solutions should I propose in this setting instead? And how much better would it be than what's suggested in these works? And I couldn't tell easily. I had a hard time. I thought, man, that sucks. Right? If Andrew's doing this nice work in this space, and I can't even figure out where I would apply it when I have a very direct problem like that, what am I left with?
So in that paper, Fabian, the objects being sent back are responses from the LLM?
Yeah. It's just the responses from the LLM. Now here, there's a whole bunch of criteria that break some of his assumptions, right? Or help with some of his assumptions, like the variability that comes back from the LLM. They do this in phases where they try to, so there's heavy dependency as the queries go on, like what else comes out, right? So it fits some of his settings actually really nice. There's a data set there. So I wasn't saying go and redo use this data set for your examples, but the setting of this, I'm like, okay, now here's a setting that I find maybe a little bit more believable than the settings of the website fingerprinting and all the other stuff that has been done. This one is a little bit more constrained. It's a little bit more believable. Hey, which one of Andrew's techniques would work best? And I can't tell.
Do you have an answer for that, Andrew, or do you want me to?
Yeah, Andrew, because you saw the presentation. So what do you think?
So I would imagine our PFG approaches would work best there, because there is I would propose that there's no way of knowing all of the sequences that could come back, because they are governed by what were you searching for, how much are you asking from
Exactly.
the LLM, and they can be quite long.
Mhm.
However, you could extract likely dependencies when this word of this size comes back, what's likely to be a word that would come back and what would be its size. So then it would likely decompose quite nicely into a graph of objects and dependencies being words.
Yeah, this is pretty much how they broke it, right? So that's exactly
Right.
what they did. Yeah. Mhm. Yeah. So, but I think it's an example, a setting that you might be able to use to frame your solution space, right? It seems very natural. It seems ones in which I was like, oh yeah, hey, the object store really doesn't know the full set of sequences. It can't really know. And there was a whole bunch of things that seemed really realistic. And then I was like, okay, which one of Andrew's things should I apply and how much benefit I'll get over A versus B? And I couldn't really tell in the setting at all.
Yeah, I mean, what I don't know to say is like knowing, like if I just look at that data set, is there a litmus test that tells me how much benefit am I going to get by looking at sequences versus not? Like just,
Not
I
yet.
mean, and that's a toughie. I don't, that's maybe that the answer there might be try them all and see what you get.
Yeah.
Yeah.
But it's valid for you to say that in your thesis, right? It's
Yeah,
valid
yeah,
for you to
yeah.
have that discussion. It's just not there.
Yeah. No, I think that's a good discussion to add in. Like I say, you may not have all the answers there, Andrew, but at least acknowledging the questions and sort of laying out what you know and what you don't know, I think might be helpful for folks who are looking to apply what you're doing.
Right.
But definitely some pretty cool parts.
Did you have other things, Fabian, you wanted to get?
No. I'll talk to you and him offline separately.
Cool.
I
Okay.
don't need.
So let's see who's next. I don't know where you guys are sitting. So Kate, you want to go? You unmuted.
Well, I have a quick question. Maybe this is naive, but so in an HTTP, let's say web-based setting, what if I just say, okay, every request has to be for 2,000 bytes, byte offsets? Like no matter how big the object is, you always ask for 2,000 bytes. You have a 2 megabyte object, make 2 megabyte divided by 2,000 bytes, different requests for different byte ranges of that object. In order, out of order, I don't care. So the client always makes a request for exactly the same amount of data, no matter how big the actual objects it's reconstructing is. Doesn't that just solve all my problems?
It does. And in fact, that's optimal. Then that would be the value of C is whatever it would take to take the minimum object to the largest object. That's then essentially you've padded everything. And so
No,
sure.
no. See, that's what I'm saying. I'm not, when I get the minimal object, I don't get the maximal object amount of data. All I'm saying is that I cut up the maximal object into n number of minimal object size objects. And I ask for them independently.
Right. So there have been techniques then that have shown that you can still, so this is really no different than packetizing, so to speak.
Right.
So there are adversaries, and they have this very similar idea has been leveraged in other works where they look at the cumulative amount of data that was requested. And so if the adversary knows that this is your scheme, then the adversary would perhaps be looking for, okay, there's been a lull in requests, and I will assume then that all of the data requested in this particular time frame was for an object. I will sum it, and then I will make a guess.
Okay.
So
then how about then, okay, so right, that's what I kind of expected you to say. Then so we start analyzing the request response timings, right?
Right.
How about if I homogenize the timings and say, I'm only going to make the same number of requests per time period?
Then So then you end up adding, and these would be then choices the adversary, the data store would have to make, right? This is going to increase latency because now it could perhaps take longer. You eventually would have to get to a point where you just are sending from the, if you truly want to mask against all types of features, what has been downloaded, the object store would basically just have to send a constant stream of data to the client. If it's small requests, then you're essentially sending as much data as you would as the big request. If you're waiting for a big request, you're perhaps encountering latency if there's some delay involved. So if that's the avenue the adversary, the object store wants to take, then I think the object store has started to drift away from.
Well, so that's, I guess what I'm saying is, let's flip it around. The object store does nothing. It just gives you the data. It's not its decision at all. It's the client's now. I'm a client. I decide how big the packets are, how smooth the requests are, and over what time period I'm going to hide my requests. See what I'm saying? Like, let the object store do nothing. Like, it will give you the whole object, the small object, this byte range, that byte range. It doesn't, it just responds. Okay, so there's no smarts in the server at all. Now I have a client who says, like, I am worried that my sequence of requests against this object store is going to reveal what kind of objects I'm getting. And different clients can worry about this problem to different amounts, right? So if I'm very worried, I can say, look, what I'm going to do is I'm going to take all of the stuff I need to get from this object store, and I'm going to turn it into individual byte range requests that look identical, and I'm going to smooth those requests over a particular time range that I am willing to pay. So the client gets to decide what's my latency, what's my so basically every client gets to tailor how much it's hiding to how much overhead it wants to pay to hide it.
Right. And so, sure, I would then say that then just becomes a different setting than what we consider here. And then also too, having that separate discussion then from what this work considers, I would again, this is a discussion for a setting I would say is different than what we consider here. But then in that setting too, nothing prevents the object store from then. So there are things like rate limiting, number of connections. These are things that object stores, websites. So for instance, even in creating some of these data sets, I had to leverage obfuscation techniques myself to download all of the objects, like creating the Node.js data set. I had to leverage multiple simultaneous Tor connections to connect to Node.js to download all of the hundreds of thousands of head requests. And I had to close the connections and start new connections from new Tor exit nodes because they were on to me and they were starting to rate limit me. So I would just counter that with, again, it's a separate setting. And then I would also be worried about object stores that are unwilling to play that game and would start to turn off clients because, hey client, you're pulling too much data because you're trying to mask and you're increasing my bandwidth overhead, and I'm unwilling to pay that price.
Good question, though. Interesting.
Thank you. Yes.
Did you want to hand the baton off, Caden?
Oh yeah, sure. That was the only question I had.
So I see Jasleen unmuted.
Yeah. So I have three small questions, and first a comment, kind of following up on the discussion with Fabian, that the last chapter seems way too lean and having much more of a discussion summarizing your contributions and perhaps adding the operational implications would make that a much more reasonable chapter. But otherwise, I enjoyed the dissertation. So my first question is, you mentioned right at the beginning that you are not guaranteeing that objects are not isolated, is the term you use, which basically means that objects can be identified. Some objects can still be identified. So do you have any, I'm not sure if I saw any of those numbers in the evaluations you showed, that after you ran everything, how many objects actually remain still identifiable?
No, we do not have those results in the tests.
I mean, I guess the closest would be your precision recall numbers for particular subset of objects, Andrew. I mean, sort of.
Potentially, but those, those were for subsets,
Mm-hmm.
right, of the data set. So no, the straightforward answer is no, we don't have the per data set, per run of the algorithm, how many objects are left completely unpadding. Now that would, that would depend, to then run those tests would depend on what was the value of C and then what was the data set under consideration.
Okay. Would that be a useful thing to try and characterize?
It could be, but again, it would be, I guess, so dependent on what is the data set under consideration. If I were an object store and I wanted to know that, I could run the algorithm and then conduct that assessment myself and maybe have like a back and forth, like, okay, well, maybe C of 1.03 didn't get us to X number of isolated objects. Maybe what if we increase our budget a little bit more, maybe we get there. That would be dependent though on the object store's data set.
Okay. Also, you don't allow any scheme that can introduce extra transfers or dummy object transfers, right? Was that simply to constrain and, contain the amount you have to explore, or is there something practical or another reason why it should not be considered?
Right. So I think overall, the intent with this work was to make our solutions as widely applicable as possible. So make the requirements of the object store as little as possible, make the knowledge that the adversary has as encompassing as possible without assuming too much. And so as part of that, the fact that we don't consider decoy objects, I would say that makes our work as widely applicable as possible, because let's say we did consider that and make that one of the hallmarks of the technique, then that would preclude any object store from leveraging our techniques if they were unwilling to add decoy objects. So here, then I would say that you could build upon our setting by perhaps adding decoy objects. It will not undermine the guarantees provided by our work, which I like to think is as widely applicable as possible.
Okay. The last question is more of me trying to get a sense of the numbers. Like your first study, you had the plot where you were comparing the PWOD and then P alpaca and POP and PRP, right? And it seemed like the differences were very, very small, especially since I guess the D alpaca was so large. Is it a significant gain over the state of the art? How would you characterize that?
So I would say if anything too, so I guess to Fabian's earlier point, this setting has been widely discussed for decades now, almost, with as part of like the proposal for this, going back and rereading some of those papers, variety of proposals, different opinions on what is the appropriate metric. So one of our, or at least I would characterize, why did we even consider independent retrievals? It was to hopefully kind of settle the science, so to speak, to say, hey, at least for a padding factor constraint overhead, this is optimal. If it's not optimal enough, then at least we have settled these are the techniques that would be optimal. I will say though, at least from these results here, what really stands out are the PWAD results, right? Where we do have, yes, these are the y-axis starts at 5 bits each, but we see across the board here, the PWAD results for I infinity, which are these whiskers, are half a bit, whole bit separation, which is quite a lot for bits. And so, if anything, I would say these results really show that PWAD is, in fact, for I infinity and for all of the benefits you get when you leverage I infinity, PWAD is, in fact, a very great technique. And then I would say going after I infinity as a metric, there's a lot to gain there as well.
Okay, thank you.
Thank you.
All right, Jay, you're the,
I don't have any additional questions. Thanks.
got it.
And
Okay.
So Andrew, just a quick thing relative to Jocelyn's comments. It's very similar to what I was saying earlier with the space and the metrics. I think you convinced me in some places that these were the appropriate metrics. I think some of the chapters, like that one on slide 15, you can have a set of recommendations, right? It's very hard to tell which things, what were the main takeaways from these chapters. Like, it was really hard. Like, I'd go back and I'm trying to figure out, like, okay, so all right, this difference seems pretty minor. Like, yeah, all right, so what? And then I get the answer like 3 chapters later. Then when we started to, it's not so very self-contained. I kind of figure out the so what, like 3 chapters after your results. And I think in some of these sections, in some of these chapters, you can have your recommendations or your takeaways there. It'll make it a lot easier to figure out what your key contributions were.
Mm-hmm. All right, well, if no one has additional questions at the moment, I guess why don't we sort of go into our private faculty breakout here?